Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're delighted to have N Linial from the Hebrew University.
Thank you. Okay, I think there are enough of you who've heard me preach in the past, so as always, feel free if you have any questions, comments, anything, don't wait till the end, just... Okay, so it's really a subject that I'm very excited about, and it's a subject that I've touched upon sometimes in the past, and I'm coming back to because there are lots of new discoveries that are relevant, and there is quite a bit that tells me that the subject is in fact even more significant than I had realized before, so I think it's worthwhile coming back to it. So I want to start from a question that, well, even in Microsoft I can say this is of real practical importance, great practical importance, which is, that's a good spot to start this, how to read large graphs. So on this issue, I don't have that much to offer except to explain to you what the problem is and why it's so important and so on and so forth. But it will serve as I think, and it is, a major source of motivation for the things that I will tell you later. So the area of science in which I see this on a regular basis is bioinformatics, which is something that I do. But it's an extremely general question of relevance to anything in machine learning. In fact, I would even dare to say that this should be a next step in areas such as statistics and machine learning and so on and so forth. So let me start from the concrete. There are lots of data, so I will stick with bioinformatics just because it's a subject I know something about, but such examples are all over the place. In any areas, you know, big data is of course the popular buzzword these days, but so to stick with to bioinformatics, for example, when you collect data about in large-scale biological experiments, one of the things that you find out is something which can be described in terms of what's called the protein-protein interaction graph. So what is it? There is some organism with which you're dealing. You don't need to know anything about anything significant about biology to know that proteins are the little machines that do anything in any living organism. And these molecules can be in interaction. I mean, this is really how things take place, but it's limited. So you can create a graph in which the vertices are the proteins of the organism in question, just to give you a scale. It's really, so how many proteins are there, let's say, in our body? It's a matter of, there are different ways to count it, which makes sense, but any number between, I don't know, 20,000 and 250,000 would make sense according to, so that's the scale of the graph. It has edges, and there it is. So, of course, this is a very meaningful source of information, this big graph. But how do you read it? I mean, what is it that you want to look at in a graph like this? Or for example, I give you this graph of a human, or this graph of a rat, or of Arabidopsis, whatever, any of the model organisms. How do you compare between them? How do you tell anything? So this is really a major question. And I must say, to the best of my knowledge, there is really no good answer for this at the moment. So it's a major question, and as you'll see, it motivates much of what I do today. I'll tell you today. So what do people do? Some of the time, so I had a heated argument with my wife, with Michal, this morning, who's a biologist. And those of you who know me better can understand how critical I was about stuff that people do in this area. And she defended her terrain, her colleagues. So I have to agree, okay, so some of these people perhaps do things which are not completely stupid, but so for example, let me start on the positive side. In biology, in systems biology is the field in which so what they do is they would, for example, introduce some modification. So perhaps feed the organism something different, or cause a mutation or whatever, and redraw the graph and understand what the differences are. That's very meaningful for their purposes. So that's one thing. But on a general level, people usually count degrees of the vertices. And why are degrees being counted? For, well, as far as I can tell, for only one good reason, that it's easy. That's the only, but it really provides very little information. So how do you, so this is a major problem. And what I want to tell you is some background for the following approach, which says count small subgraphs. So I'm not claiming that this is not even close to an ultimate answer to this question, but at least it's a meaningful and possibly useful, at least partial answer to this. But before I go to this and I explain where this is coming, and first of all, I have to say again, in defense of biologists, system biologists, that this is something that biologists do carry out to some extent, that you'll see this idea in bioinformatics papers. But even what to do with these numbers, even that is not so clear. But let's back up and again, stay with this extremely important question and ask ourselves, really, what should be done about this? So I think a good place to start is really what the statistics do. Really, let's go back to ancient history when the field just started. So you're flooded with some large number with lots of numbers. And what do you do? Okay, that we already know. All of us know what to do with this, right? I mean, perhaps you'll see that the numbers come in clusters. Perhaps you'll recognize that it looks like a distribution that you know, and okay, perhaps you are now able to estimate, give good estimates for the defining parameters of and so on and so forth. And I can imagine something like this in this context as well. So a possible general approach would be come up, so in analogy with what I just described, come up with a family, hopefully not too big, of generative models. Can people see this here, or should I? Yeah, you're still okay. Generative models of graphs. And recover. So somehow it's strange for us to, if you really understand the protein interaction of a human, you've really made huge progress in biology. We don't understand exactly what this means, but for example, one thing you could say, okay, let me come up with some simple models. This is like the standard distributions that in analogy with the standard distributions that we consider in probability, in statistics. And then let me find out what the defining parameters are for this graph. So that's an approach. And now I want to mostly concentrate on this. So a good reason to look into these problems, and one of my main motivations for coming back to this question is this theory to a large extent developed originally here, mostly by Vatsilovas and co-workers. Anyone here? Anyone who? I don't think so. But so he has. I should have brought it down. He has a beautiful book on large networks. And graph limits. Which to a large extent tells you, or to some extent tells you, that if you understand the count of small subgraphs in a big graph, it really puts you it really carries you some way along what I wrote here. That it really tells you if the graph comes is a sample from a big distribution of graphs, then it gives you a good hint of what this limit distribution is. So just to, I don't want to I certainly don't have time to develop this whole thing, and it takes many hours to easily, this is already by now a subject for easily a one semester course. I'm not going to try this, but if you never saw this, let me just give you one very important theorem from, even I won't even formulate it precisely, but I'll just give you a hint on what this main theorem is. Main theorem in this area. You would like somehow everything that we do here today is asymptotic in nature. We only speak about very large graphs. So you have a sequence of graphs, and you'd like to have a notion of what it means for the sequence of graphs to tend to a limit. Now, as you all know, if you have a metric, then it's possible to speak about limits, if there is a metric on whatever object, because then at least you can speak about Cauchy sequences and then perhaps understand more what's going on. So how do you need a metric among graphs. How do you compare graphs? Well, it's easier to think of a graph as just a symmetric 0, 1 matrix, or if you want a mapping into 0, 1 of the integers, think of this as black and white dots, so a mapping into 0, 1. So instead, let's explain what is the metric between two functions, symmetric functions from 0, 1 into 0, 1. Well, I allow you to rearrange in a symmetric fashion, apply a measure-preserving map on the unit interval, and then I take these two functions and I take their L1 difference, something like this. So there is a good notion of distance among graphs, and so the theorem says that a sequence, and this is called the square or cut metric. So a sequence of graphs has a limit in this sense if and only if for every fixed graph H, Gn, the frequency with which H is found in Gn tends to a limit. So you have two notions of limits here, and the theorem tells you that they coincide. One notion comes from this way of comparing or measuring distance among graphs. And the other comes from this concept of counting small subgraphs. So you fix a graph H, and you ask, how often do I find this graph H in Gn? Okay, I'll be more accurate with the details a bit later. And if this tends to a limit for every graph H, then it makes sense to say that the sequence goes to a limit. The two concepts coincide. Okay, these two notions of So in particular, what I'm trying to read out of this in the context of this very general question is that if you understand the frequency at which you see small subgraphs in a big graph, then this tells you what the limit object is. There is a lot of additional stuff in graphons and whatnot. It's as I said, by now already a big theory, but that's at least a good motivation for, okay, let me say two more things about this very general context. First of all, this is also very closely related, but I will not develop this local approach. So the notion of local, which appears in my title, is exactly this, and I'll say much more about. Property testing, for those who know what they are, is very closely related. That's another way to understand or to view the local structure of big graphs is related. We're also going to talk about other combinatorial structures, not just. I will mostly focus on graphs, but we will also see, just briefly at least, two other types. One is tournaments. A tournament is just an orientation of the complete graph. And again, you can look at small subsets and ask how often do I see everything that I see. And I will also speak about permutations. And in general, any large combinatorial object that you can think of, you can also associate with it a local theory. So I have to explain what is the local structure of a permutation. So a permutation, think of the permutation as, in Sn, as the numbers from 1 to n written in some order. And then let's say I want to understand the 5 profile of this. That's an expression I will introduce in a minute. So I'm looking at some 5 locations here. I see here a 5 tuple. It has an order. There is an order. This is bigger than that and smaller than that and so on. So it gives you a permutation, induces a permutation on 5 element. So on S5. So permutations also have a local profile. So that's so this is one comment. The other thing is there is more to local in the sense of looking at neighborhoods. That's also very interesting, but I'm not going to get into this at all. You could also ask, instead of saying I'm looking at, let's say, 5-element sets or something like this, I'm looking at a vertex and I'm looking at what the 5 neighborhood of that vertex looks like. That's also very interesting, but I'm not getting into that at all. Those of you who heard me ask the question about girth in lunch, that question can be, belongs very naturally into this area. Okay, so what are we doing? We are going to have a large graph, and we are going to look at so most of the time, as I said, I will speak about graphs. We're going to look at k-element subsets. So this is called the k-profile of a graph. So G is a large graph. K is an integer. The k-profile of G is this. You're looking at all the k-element subsets of vertices. Each k-element subset spans a k-vertex graph. So this induces a distribution on k-vertex graphs. This distribution is the k-profile of G. Okay? Good. And what do we want to look at? There is a whole array, no, not too many, but there are several possible behaviors or key properties of the profile that we. So in fact, let me already start with one very concrete and very difficult question about which we know still very, very little. And I will try to tell you a few of the things that we know. So here's what I view as a very basic question. What are possible K profiles? Just very concrete question. So let me be even more concrete, just to bring home to you the notion that these are very basic questions, and at the moment we understand them very, very poorly. Let's start with k equals 3. Okay? Just k equals 3. So what are possible graphs on 3 vertices? There is this, there is this, and there is this. And let's say I call this probability P0, P1, P2, and P3. So if this is G, then and this is P of G. This whole vector is P of G. And I'm not interested in what happens with small graphs. I'm only interested in the asymptotic. So in particular, I'd like to understand this set, this 4-dimensional set, which consists of all the x's in R4, such that for every positive epsilon and every large n, there exists an n-vertex G such that P of G minus x is less than epsilon. So, I mean, don't let this confuse you. Basically, which 4 tuples am I interested in? Those which are realizable, or almost realizable, I'm allowing an epsilon error, by arbitrarily large graphs. So think about it. This is a 4-dimensional set. In fact, it's only 3-dimensional because, of course, the coordinates are non-negative and sum to 1. What is this set? I mean, are we able to describe it? The answer is no. We are still unable to describe even this very simple, or this first case of the general problem. I will tell you a few things that we know about this. And as I'll try to impress on you, while this is still, I mean, it's conceivable that this is, if we really wanted, anyone who's interested in this would now be working on this problem and would like to understand this set. The case of k equals 3 perhaps is manageable. But when you go up to k equals 4, the situation at the moment is really bad. We really don't understand the thing at all. So let me try and, why you're not awake enough in my, I'll try to make you awake. Let's see, can I do this? Okay. Okay, so let me try and give you an impression on a. So here is a very well-known and old fact. Goodman's inequality from 1964 says that P0 plus P3 is at least a quarter. So let me just be accurate about this. I actually should be writing minus little o of 1, but because I'm dealing with this, I'm suppressing such terms. Let me prove this to you. So at least we prove something. It's really very easy. And instead of speaking about P0 and P3, let me instead think of, instead of speaking about graph, what I do is I color the complete graph on n vertices. The edges, I color them blue and red, okay, instead of edges and non-edges. And so, first of all, before we prove this, let's see that this makes sense. If I do the coloring at random, or if I take a GN1/2 graph, the chance for this is an 8th, and the chance for this is an 8th. So at least you have equality here. And how do you prove this? It's really very easy. So let's sum this expression. On the one hand, this is maximized. Of course, these two numbers add to n-1, so this is less than n times n-1 squared over 4, which would be the case if each one of those is n-1 over 2. On the other hand, I can sorry, yeah, to guess correctly. But there is another way to interpret this. You see, let's instead now draw things like this to indicate color. You see, every triangle like this contributes 0 to this. Every triangle like this contributes 2 to this. So this is 2 times n choose 3 times P1 plus P2. And now we just move things. Now it's just high school algebra, and you get this conclusion. Okay, very good. So this nice observation, this fact has been known, as you see, for almost 50 years. So what about if we go up to 4 vertices? Okay, let's ask the same question for 4 vertices, and let's see what we know. And that will give you an indication of what the situation is with it. Okay, so for want of a better name, let me call them Q0 and Q6. So this is the probability that I get 4 vertices with no edges, and this is the probability that I get all 6. Of course, there is more than 7. There are, in fact, 11 different isomorphism graph classes for graphs with 4 vertices. So in view of what we saw here, and the fact that equality held exactly in GN1/2, this made Erdos conjecture that Q0 plus Q6 is at least 1 in 32. Let's just go over the calculation. In GN1/2, the probability of this is 1 in 64, 1 in 64, 1 in this is not true. It was refuted by Andrew Thomason. And there is he wrote about this more than one paper, and there is also Peled and students also found counterexamples. And the point is, so one of the main observations that really motivate my work on this is the fact, look, in any mathematical field, your understanding depends very much on examples that we know. And there are really very, very few examples that we know. I mean, concrete classes of graphs that we understand. So the answer is smaller than this. Not much smaller, 1 in 33 or so. But no one has any guess on where the minimum is. So what is this hiding? I will tell you later more about what's known here. And one reason why this is more, than a side anecdote. So, okay, there was this question, the conjecture, the natural conjecture is not true, is that think of very fundamental questions like Ramsey's theorem, the quantitative Ramsey's theorem. So, you know, RKL is the least integer such that if I take the complete graph on this number of vertices and I color everything blue and red, then either I get a blue k-clique or a red l-clique. And what do we know about these numbers? So let's speak mostly about R and N. The asymptotics here is something like 4 to the n. And here it's root 2 to the n. So it's a 4th power. And the lower bound, the best lower bound that we know for Ramsey numbers comes from Gn 1/2. And to me, this suggests that perhaps this is not the right place to look for the solution. That there are graphs which have better behavior in this respect than random graphs. So this suggests to me that there is really a new continent to discover here. You know, there is a whole class and the fact, at the moment, no one even has a guess of where this is. I mean, granted, the difference here is not so big. It's really, okay, so we know now lower bounds, I forget, perhaps 1 in 34, something like this. The gap is not so big. But the point is, no one even has a concrete guess on where what the optimal construction is. So we know, so it's like the famous story about the elephant. There is an elephant in the room. We've touched it somewhere, but we don't understand, you know, what shape it is, what size it is, where it goes, and so on. So this is an indication that there is an elephant to discover here. By the way, Yuval, what is the situation about timing? When should I, for what? Okay, good. So, okay, so let me then try and give you one more indication on how poorly we understand these things and what other continents there are to discover. So here is a very interesting and basic notion that's related to all of this, and this is inducibility. So we're fixing a graph H, and this is the largest frequency with which we can find an induced H. So I'm a little sloppy here with my definition, but I think you understand. So you fix an H, you take a large graph, and you want the probability. Let's say that H is a k-vertex graph. I want a big graph, in which I have the highest probability that if I pick k vertices, what I see is an H. Okay? And there are certain graphs for which we know this, but mostly we don't. So here is a nice example. I don't know how much I will be able to cover the details of this, but let's say H is a C5. Okay, I'll get you doing something. Which graph has the most induced C5s among all big graphs? What would you do? What would you guess?
Blow up of a C5.
Blow up of a C5, okay. Excellent first guess. Still not final. So that's a blow up of a C5, just for those who don't know the terminology. So you replace each vertex of a C5 by an independent set of size n, and you connect with a complete bioinformatics graph. How likely are you to find a C5 here? Well, you'll find it precisely if all the 5 vertices, each vertex falls in a different block, which means that the probability is 5 factorial over 5 to the 5, which is 24 over 625. Well, anyone willing to raise the bets? Anything better than this? It's a good start. I mean, the solution is not so far off. What can you do to improve it even locally? What if they all fall in the same block? Now we're getting nothing for this, so just recurse. Recurse, you just do the same thing. And if you do this, you get 1 over 26. So the inducibility of C5 is at least 1 over, okay. What do we know? So I forget the exact number, but this is what we know at the moment. I don't know how much time I will have to tell you about this. Let me only say 2 words to explain this. This comes from flag algebras. So if you know what these are, then you know. If not, I hope to be able to say something. This is a beautiful method that Razborov has invented a few years ago. It has a theory, and finally you go to the computer and compute. You have to solve some large, growing semi-definite programs. At some point, of course, the machine gives up. And this is what the solution, that's the best we're able to do. So the barrier here is just the computational power of our machines. And sometimes in situations like this, people have managed to be clever enough and throw away that part and actually find. In short, as mathematicians, we don't know the answer. As human beings, of course, we know the answer. That's the answer. Okay, so perhaps it's not perfectly satisfying, but let me show you the following embarrassing thing. What is the inducibility of this guy? No one has a guess. In terms of numbers, the numbers are not so, the upper and the lower bound, I don't remember what they are. It's not so important for the moment. The upper and the lower bound are not so different from each other. But no one has a guess again. So for me, that's a close cousin of these things. So it's again an indication that there is a whole family of graphs that should be very interesting. This sounds like a fairly basic property of a graph. You want, that's by the way self-complementary, so the complement of this is the same graph. How can you gain in induced copies of this guy? No one has a clue. Okay, so somehow I thought I had more time. I prepared more or less material for a whole semester course. So I knew I was not going to cover everything. So let me see. What will I tell you and what will I skip? Okay, let me say a few words. Okay, there are a few important ideas that I still want to get through. So in terms of this local structure of graphs, first of all, this whole thing is very closely related to very highly developed part of combinatorics, extremal graph theory. In extremal graph theory, you mostly ask questions such as, a graph is such and such density with so many edges. Does it have to contain this and this graph? So I think you presumably all know Thuan's theorem, which says that if the density of G is bigger than R minus 2 over R minus 1, then G contains a KR. Okay? The first example is this. The complete bipartite graph with 2 equal sides doesn't contain a triangle, and that's the graphs with the highest density which doesn't contain a triangle. You want one that doesn't contain K4, take 3 equal parts, and that has the highest density. And so this local theory of graphs, this kind of stuff, contains, this is a huge extension of this basic question, because here we're only counting density, and here we want to understand the full view. So there is of course, a lot of material in extremal graph theory that's highly relevant. But this really takes a much broader view of graph theory from extremal perspective. And so let me say a word about flag algebras and so on. So this is, of course, a very basic theorem of graph theory. And this has led to various questions. One, for example, if you never saw this, then this is still a famous, one of the most famous open problems in combinatorics. Turan's problem for 3 graphs. So, question, what is the highest? So it's the analog of this theorem. What is the highest density of a 3 uniform hypergraph? So collection of triples that does not contain k for 3. So it doesn't contain 4 vertices and all the 4 triples in it. That has been open for many years. There is a concrete conjecture which I will not say, but that has been open for many, many years. One of the most famous problems in in order to attack this question and attack another question in this area, so here in particular that was already known to Mantel. So Mantel is a predecessor of Turan's theorem, says that a graph, I'm just repeating what I wrote here, a graph with density bigger than 1/2 contains a triangle. And the bound is tight. So the question that remained here is if the density of G is T, bigger than 1/2, how small can P3 be? So what's the smallest density of triangles? So in order to attack these two questions, Razborov invented his theory of flag algebras, which I will not have time to explain to you. Conceptually, it's quite simple, but very powerful. And I already explained a little bit about how you work with it. Eventually, you have to solve some growing semi-definite programs. And with this, he was able to this was completely resolved by Razborov using flag algebras. And here he made the most progress, but this is still open. So that's a very powerful tool that we're able to use in this whole area. But as I said, it's still many things remain open. So what I'd like to do in the last part of my, well, I haven't gotten even to tell you anything about our results, but never mind, that's not so important. Let me say a little about local to global. Okay, so I think having given you the impression that the local theory of combinatorial objects is hard, deep, interesting, what's perhaps even more exciting is the local to global theory. So my main question so far has been, what does the K profile of large graph look like? What can we say about this? And as I said, with K equals 3, well, there is perhaps still hope. I didn't tell you some of the theorems that we were able to prove, but we were making progress there. 4 seems at the moment, getting a full description of the 4 profiles seems at the moment completely out of reach. But then there is another kind of theory that you could ask yourself. So let's suppose I'm telling you the k-profile of a graph. What can you conclude globally? So here there is a beautiful conjecture by Erdos and Hajnal. Okay, so let me start with a definition. There are several general properties that you can consider and are interesting about profiles. Okay. There is one class which is very interesting and again worthy of a separate lecture, which is quasi-random. An object can share properties with a random graph, and there is again a beautiful theory about this in graphs and so on, in permutations. At least I should mention the name of Chang, Graham, and Wilson, who developed such a theory for graphs, and then more recent work on permutations and so on. So that is something we have a fairly decent understanding of. There is another property of genericity, which is much weaker, which is universality, k-universality. You say that G is k-universal if it has a full k-profile. So everything is there. So that's another very interesting property to consider. And this is what the Erdos Hajnal conjecture speaks about, and it's really an amazing conjecture. So here it is. For every h, fixed h, there exists an epsilon positive such that if G is an n-vertex graph, so n is large, and its independence number, so the largest independent set, and its clique number are less than n to the epsilon. Sorry, I got it wrong. That is h free, then alpha of G and omega of G are bigger than n to the epsilon. So let's look at this and understand. So this is a graph which is not universal at some level. If you're looking at the local profile, there is something missing. There is no H induced, right? H free means doesn't contain an induced copy of H. Now, in general, I mentioned to you before the Ramsey theorem. I mean, if you reverse the way that I told you before, then every graph on n vertices has either a clique of size log n or an anticlique of size log n, and the bound is tight. It's attained in a random graph. If you only omit this one object, there is no H in it, then the numbers jump from logarithmic to polynomial, to a fractional power. In fact, in their paper, they prove exponential in root log n. So that is known. But n to a power is open. The first case, which is unknown, is h equals C5. We don't know how to prove this or refute this for C5. And just to give you a sense of, I said that I will mention tournaments, so at least I should mention them once. So Alon, Pach, and Shoimoshi proved that Erdos Hajnal for graphs is equivalent to Erdos Hajnal for tournaments. It requires some explanation. So what it means for a tournament to miss something, you understand. Let's say we're dealing with the 7 profiles, so there is some tournament on 7 vertices which you cannot find anywhere. What replaces this, the analog of this, is the largest transitive sub-tournament. So that's very easy. Every n-vertex tournament, if you never saw this, then that's a good exercise while you shower or something. Every n-vertex tournament has a transitive subtournament on at least log base 2 of n vertices. The bound is tight up to a constant here. Okay. So these two theorems, these two statements are equivalent, and they're both open. And let me just, to give you, perhaps I'll finish with that. Let me tell you, so at least I will mention one small thing that we did. So a different way of stating the Erdos Hajnal conjecture, that's a restatement of the conjecture, which is nothing. I'm just manipulating simple things. It says for every k, there exists an epsilon positive such that if alpha of g and omega of g are bigger than n to the epsilon, smaller than n to the epsilon, sorry, then G is K universal. So we're wondering if there is this is something of the sort that it's a weak version of what you expect to see in a random graph, okay? And so we were wondering if there is anything like this, instead of saying that there are no large cliques and no large anticliques, perhaps if the counts are small. So here is a very simple thing, which, I mean, it's simple in the sense that it's just work. There are no really any ideas necessary. So proposition that I proved with Avraham Morgenstern. So coming back to the triple statistics, if P0 and P3 are less than 0.159, then G is 3 universal. The bound is tight. For example, we know that this does not imply 5 universality. We don't know whether it implies 4 universality. And this is a new type of question that's very recent in this area. So let me just say, so why, let me just say one more thing about why I find this conjecture so exciting. There are really lots of things. In particular, think of, perhaps it's not the right time to do this at the last minutes of a talk, but think about what we know in physics. In physics, all we know is really, all we have to start with is local information, right? How particles interact. And we'd like to conclude for it a big picture of the big view of the, and this, I think, this is why I find this conjecture so exciting, that all we are saying is that if you look at the repertoire of the small size subgraphs of this big graph, this has this huge effect on the overall structure of the graph. And with this, I will stop. Thanks.
Questions or comments?
Was it a recent paper that claims to have solved this conjecture? 150 pages.
150
A long paper.
There was one a few months ago, which my understanding has been found to be, I don't think it was so big, so perhaps it's a new, how old is this? You remember the name or? Okay, so there was, I'm aware of a paper from a few months ago which claimed to have proved this, and I didn't read it, but I checked with, one person that the author thanked was this guy, Janos Pach, so I checked with Janos, and so my understanding is that the question is still quite solidly open.
There's nothing else. Thank you.